This lesson is part 1 of section 7.6. Today we're going to be talking about the factor theorem. So the factor theorem is a new method now for learning how to factor polynomials. Now this method is supposed to be your last resort when you're trying to factor a polynomial. So if you don't recognize a difference of squares or a sum or difference of cubes, if factoring by grouping won't work, then you use the factor theorem. So it's kind of like the quadratic formula. When you were solving quadratics, we would ask you to use either factoring or the square root method before you try to solve using the quadratic formula. So again, the factor theorem is a new method for factoring a polynomial, but it's one that you want to use if nothing else works. Alright, so our objectives for today are to identify the possible rational zeros of a polynomial function and to find all the roots of a polynomial function. So these probably are brand new terms for some of you guys. This one should not be a brand new vocab term though. A rational number is just a number that can be written as a ratio. So take the number 3, we can write that as 3 over 1. So anything that can be written as a ratio would be a rational number. And in just a second we'll talk about zeros and roots. Alright, so let's define what a root is. Now to the right I have a graph of this polynomial function here. So see how the polynomial function crosses the x-axis at 3 different points? Those are called the roots, or the zeros, of the polynomial function. Now we've been calling them so far in this course x-intercepts, or solutions to the equation. If we were to set this equation equal to 0, that function here, x cubed minus 2x squared minus 5x plus 6, if that were to equal 0, then we would find the solutions by finding the x-intercepts. So all of these things mean the exact same thing. All of these terms are interchangeable. But what we're looking for is, we call them zeros or roots to this polynomial function. So I have zeros at -2, 1, and 3. Alright, now down below I've already worked out problems 1 and 2 just to save time here, but these are review questions. Now in the first question I ask to factor this completely. Now as you can see, I took out a GCF first and then I factored the remaining polynomial, and the factors of 2x squared plus 8x plus 6 are these individual factors here. Now when I ask you to solve by factoring, you're still using the same method where you find your factors, but then we ask you to take it a step further and you find solutions, or zeros, or roots. So these here would be called the roots or the zeros of this polynomial function here. So notice a big difference. Here we're solving, we're finding individual zeros or roots. Here we're just finding the factors, but they are related. Our roots came from these particular factors. So there is definitely a relationship between zeros and factors. Now we definitely see a clear relationship between zeros and factors. So if we had a 0 of 2, that means the factor would have had to have been x minus 2. If we have a 0 of -3, then our factor should be x plus 3. And if we have a factor of x plus 6, our 0 would be -5. A 0 of 5 means our original factor was x minus 5. And if we have a factor of x plus root 7, a 0 would be -root 7. Alright, now in question 4 here, we're asked to take this polynomial and we're asked to divide it by x minus 2. Now I know I can use synthetic division here because I have a linear binomial, so I'm going to pause the video and I'm going to use synthetic division here to divide that polynomial. Now in this case I end up with a remainder here of 16. The next question says to evaluate f of 2. If I evaluate f of 2, I have 4 times 2 squared minus 3 times 2 plus 6. So I plug that 2 back into the original function and I have 4 times 4, 16, minus 6 plus 6, which ends up giving me 16. So the big question is, how is the value of f of 2 related to the remainder we got in part A? Well, clearly they are the same. And this leads us to a big theorem that we're going to now use that relates to the factor theorem. So the remainder theorem states that when a polynomial, f of x, is divided by x minus r, then the remainder is f of r. So we took a polynomial here, f of x equals 4x squared minus 3x plus 6. We originally divided it by this linear binomial, which represents this x minus r. We noticed that the remainder, this 16, is also the same value as f of 2, or f of r. So in other words, if you take a polynomial, you divide it by a linear binomial, Remember, we put that the opposite of r here. And we end up with this remainder, which is also equivalent to if we just took that number, 2, in this example here, and we placed it inside the function and evaluated f of 2. So our remainder theorem now leads us into something called the factor theorem. This is exactly what we're going to be using today to factor polynomials. Now this factor theorem states x minus b is a factor of f of x. So x minus b is a factor of f of x if and only if f of b is equal to 0. So this is a very mathematical definition for us, and I'm going to break it down. Hopefully this will make a little bit more sense. If you have some factor, x minus r, okay, so we know x minus r is a factor, then we also know that f of r has to equal 0. And if we know that f of r is equal to 0, so if we're given this information here, then we can automatically assume that x minus r must be a factor of f of x. So in other words, if we have some value r, we try to use synthetic division, we should end up with 0 here as a remainder if x minus r is supposed to be a factor. All right, let's test our understanding of the factor theorem by answering questions 5 through 7 here. Now question 5 asks if 2 is a root of x cubed minus 4x squared plus 3x plus 7. Now we know based off of what the factor theorem states, if 2 is a root, then f of 2 has to equal 0. We also know that if 2 is a root, x minus 2 would have to be a factor, which means we can use synthetic division. We can place a 2 here on the outside, and we would expect to get 0 as our remainder once using synthetic division. So in order to save some time here, I'm going to pause the video and I will evaluate f of 2, and I will also do the synthetic division using that factor x minus 2. Now as you can see, when I evaluated f of 2, I ended up with f of 2 equaling 5. When I used the factor x minus 2, and I placed that 2 here on the outside of that synthetic division bar, I ended up with a remainder of 5. Now what this is saying, according to the factor theorem, is that 2 is not a root then. So 2 is not a root because we don't get our indicated value f of 2 equaling 0. So we don't end up with f of 2 equaling 0, so in which case 2 is not a root. Okay, next up we have question 6, and this one asks us to find f of negative 3 in order to determine whether x plus 3 is a factor of this particular polynomial function. Now we know that if we make that substitution of negative 3 into our function, we should expect this to equal 0. If it is equal to 0, then we can decide that x plus 3 would be a factor. So I will let you guys try 6 and 7 on your own just to test to see whether or not you understand this idea of the factor theorem, so go ahead and check with the key. Alright, now in the next portion of the lesson, this is where we're actually going to be using the factor theorem and working on objective 1 and objective 2. So our first objective is to be able to list all of the possible rational roots of a polynomial function. What we're going to do is actually look at our original polynomial that we were given on the front side of our notes. And the reason why we're using this one first as our example is because we already know what our zeros are from our graph. Remember, we were given a clear picture here, and it kind of looks something like this. But we ended up with 3 distinct zeros. We had one at negative 2, one at 1, and one at 3. So those are the zeros of your function, which then would lead into factors of x plus 2, x minus 1, and x minus 3. Now we were lucky that we were given a graph because that made our job very easy to find our zeros and our factors. But in your problems, when you're asked to factor, you will not be given a graph, so you'll have to be able to find them algebraically. Alright, so our very first step in finding the zeros of our function algebraically is going to be to list all of our possible rational roots first. So again, this is relating back to objective number 1. Now, in order to list your possible rational roots, you need to look at the factors of your constant term. So in this case, our constant term is 6, and we look at the factors of our lead coefficient, which in this case is 1. We call these our p over q values. So here, p is defined as your constant term, and q is the lead coefficient of your polynomial. So we're going to make a list of all of our p over q values. Okay, remember p over q. All right, now the p values here, again, are factors of your constant. So the factors of our constant are positive or negative 1, 2, 3, and 6. Now typically you probably have only considered positive values as factors, but remember negative 1 times negative 6 also would give you 6, so that's why we can include all of the negative values here as well. Now for the factors of your q value, this is just going to be positive or negative 1, so that one's kind of a boring one. But now you just simplify this list. So to simplify this list, you take every single number in the numerator, so we start with 1, and we divide that by the number in the denominator. So we only have one number in the denominator. Usually there's many, because there's more factors of, like, let's say 4 would have 1, 2, and 4 in the denominator. I'll do a problem like that in a second. But for right now, we're just going to take that numerator, divide it by every number in the denominator. So we get positive or negative 1 when we divide 1 by 1. Then we move on. Once we are finished with every number in the denominator, we move on to the next term. We have a 2 here. So we divide 2 by positive or negative 1. We still end up with positive or negative 2. Instead of writing it each and every single one with a positive or negative sign out in front, you can just write it once out in front of the list. So I have positive or negative 1 so far, positive or negative 2. And then, of course, I move on to 3, and I end up with the same thing. So that's kind of a little redundant. But this represents the list of your possible rational zeros. Now, what we do next is we test every single one of these values inside of our function using, the factor theorem here to find out which of these are our zeros. So we would test f of 1, f of negative 1, f of 2, f of negative 2, f of 3, f of negative 3, f of 6, and f of negative 6. So clearly this is pretty tedious. Okay, so today we are going to give you the hint that in all of our problems we're going to be using either positive or negative 1 as your zeros. So in this case, I'm not actually going to show every single one of these values, but remember we had zeros at negative 2, 1, and 3. So we can assume then that f of negative 2 is 0, f of 1 is 0, and f of 3 is also 0, which means that f of negative 1 should not equal 0, f of 2 should not equal 0, f of negative 3 should not equal 0, because all of those values are not zeros of your function. You can see it clearly. Negative 6 is not where your polynomial crosses the x-axis. So we're kind of cheating a little bit since we already know the zeros of this function since we have a graph. But basically tomorrow what you'll be expected to do is fill in and evaluate f of 1 and f of negative 1 or any of the other possible rational roots inside your polynomial and then find a 0. So here we're going to cheat, like I said, and we're going to just steal this idea that f of 1 is a 0. Okay, so here is the second objective. Once you find your 0, remember f of 1 is equal to 0. Oops. So that means that x minus 1 is a factor. So once you know a 0 of your function, you are then going to use synthetic division or long division, but I bet most of you would prefer synthetic division here. You're going to find other factors. So we take our original polynomial, I think it was x cubed minus 2x squared minus 5x plus 6, so those would be the coefficients here. And I'm going to place a 1 on the outside here, okay? Now, I then use synthetic division, so here I would end up with a remainder of 0. If I don't end up with a remainder of 0, this is kind of an area where I can check. Either I messed up in my synthetic division here, or this is not actually the case that x minus 1 is a factor. A lot of times students will get confused about putting a 1 here or a negative 1. Remember, if it's a 0, the 0 goes here. Okay, so f of 1 is a 0, which means 1 goes here. X minus 1 is the factor then, so we put the opposite of negative 1 here. So there's two ways you can check that number. But anyhow, if you don't get a 0 here, you either messed up on your factor or you put the wrong number here. So, just be careful about that. All right, now, when you look at your synthetic division, this represents a polynomial of 1 degree less than your original polynomial. So we had x cubed minus 2x squared minus 5x plus 6. This represents a quadratic function then, x squared minus x minus 6. So it has a degree 1 less than this. Now this is something I can factor on my own. So the idea of the factor theorem is that you break it down into a function that you can then factor, usually a quadratic, all by yourself. So here I don't need to continue using the factor theorem. Here I can just factor this polynomial like normal. This would factor into x minus 3 and x plus 2. So to answer this final question here, the factors of x cubed minus 2x squared minus 5x plus 6 are x minus 3, x plus 2, and then we can't forget about our original factor here. A lot of students will forget this one, and x minus 1. Again, if you want to check to make sure that this is correct, see how I can multiply negative 3 times 2 times negative 1? I should end up with this constant term here. If I multiply the first terms, x, and x, I end up with x cubed. So this is definitely a reasonable answer, first of all, but it also matches what we saw here in the original problem on our front side of our notes. Okay, so this is how we're going to factor now when we can't use any other method. So again, this is a last resort when you can't use factoring by grouping or difference of squares or sum or difference of cubes. All right, let's try the next problem. All right, in example 2, we're asked to factor this polynomial. It's cubic, and it has 4 terms. Now, when we are using factor theorem, you don't want to use it right away because your first goal should be to try to factor this using the normal methods that we've used already, like grouping 2 terms together and 2 terms together. This would not produce anything successful for me, so I would not try to group 2 and 2. If I try to group 3 and 1, that also doesn't create anything for me, like a difference of squares, and neither does grouping 1 and 3. So that's why in this case, my last resort is to use the factor theorem. I have to use the factor theorem here. But on other problems, you should look for other methods of factoring before you resort to factor theorem. Okay, so anyhow, in this problem, they're giving us a bit of a hint because they tell us that f of negative 2 is equal to 0. What that tells us then is that x plus 2 must be a factor. So that will help us now in continuing to factor this particular cubic function. But I want to start here with A, which asks us to list all of the possible rational zeros. Remember, we want to take our values P and Q. We find the factors of P over Q, and we list all of them. So we take positive or negative P over Q. So let's list the factors of P. The factors of P are positive and negative 1, 2, 3, and 6, while the factors of Q are positive or negative 1, 2, and 4. Now, we have to make sure we're dividing those values. So basically what you do is you're going to run through each value. We're taking 1 now, and we're going to divide it by each of these in the denominator. So if we divide 1 by 1, we get positive or negative 1. If we divide positive or negative by 1 by 1, or I'm sorry, by 2, we get positive or negative 1/2. So we are creating alternative values here. So you want to make sure you're not just listing it like this. You want to write out each value. If we take positive or negative 1 and divide it by positive or negative 4, we still get positive or negative 1/4. Okay, I'm not going to write each of these as positive or negative in front because I know that each of them should be positive or negative. So I'm just going to list them like this. But realize that this applies to every single number in that list. Okay. All right, now we're done with 1 because we've divided each of those by the numbers in the denominator. Then I move on to the next number. If I take 2 and I divide each one of those, the first time I get positive or negative 2, but the second time I end up repeating 2 divided by 2 is the same as 1, so I don't need to even try that value here. Okay? 2 divided by 4, same thing. I end up with 1/2, so that value is repeated. I move on to the next value. 3 over 1 gives me a unique value, so I'm going to write that one in. The same with 3 over 2. So if I divide 3 by 2, I get 3/2, so positive or negative 3/2 is another possible rational zero. And also 3/4 is another possible rational zero. Okay, so I'm done with 3 now, and I move on to 6. If I divide 6 by 1, I end up with 6. If I divide 6 by 2, though, I end up with 3. So I repeat that value. I don't need to write that in again. If I divide 6 by 4, I end up with 3/2. Again, I don't need to repeat that one. So this is the list here, the complete list of all of the possible rational zeros of this particular cubic polynomial. Now let's try to factor the polynomial. So part B is actually going to be a little bit quicker here. In part B, I already know that one of the factors is x plus 2. That means I can use synthetic division here. I'm going to place a negative 2 on the outside, and I'm going to take the coefficients here and write them all in. I'm going to do this factoring real quick. I'll pause. Alright, as you can see here, I end up with a 0 for my remainder. Now if I didn't get a 0 for the remainder, then that would mean that x plus 2 is not a factor. But since they're telling us that it's a factor, and if you don't get a 0 here, you must have made a mistake somewhere in your synthetic substitution, okay, or your synthetic division. Anyhow, remember, this ends up being a polynomial here, 4x squared minus 13x plus 3. This is now one of the factors of 4x cubed minus 5x squared minus 23x plus 6. So in other words, I now have one factor of x plus 2, and then I have this quadratic polynomial left over, 4x squared minus 13x plus 3. Now my goal next should be to continue to factor this. I don't need to use factor theorem though, because now I've made this into a really easy problem for myself. This is now just a quadratic that I can factor, and in this case I can split the middle term. So I need two numbers that multiply to 12 and add up to negative 13. Those two numbers would be negative 12 and negative 1. So I split that up into negative 12x and negative 1x. And then I factor by grouping. Okay, so I'm splitting the middle term here, factor by grouping. So I have 4x as my GCF. I'm left with x minus 3. Pull out a negative 1 here, and I'm left with x minus 3. Now, I am going to continue to write that x plus 2 here on the side because I don't want to forget about that original x plus 2. Many, many, many times I'll have students who forget to write out the original factor that came from here. Okay? Remember, you're taking the negative 2 here and placing it out on the side because you're saying x plus 2 is a factor of this polynomial. All right, we're almost finished with this problem. We end up with x plus 2 here. From here, I have 4x and negative 1 that I can group together because I take out the GCF of x minus 3, and I'm left with 4x minus 1. So this is the factored form for this cubic, way up here. All right. Now, again, when you end up checking your answers, you should look for one thing in particular. These numbers here should always multiply to your constant term. Okay, so your constant term here can be quickly checked. Negative 1 times negative 3 times 2 gives me a positive 6. Also, if I look at the first terms and I multiply all of those, x times 4x times x, I should get 4x cubed. So that's a quick spot check to make sure that your answer is actually factored correctly. All right, let's move on to example 3. All right, in example 3, we're going to factor this quartic polynomial here. And we are using the factor theorem in this case because all of our traditional methods of factoring don't hold up against this problem. We can't use difference of squares, we can't use sum or difference of cubes, we can't take out a GCF because there is no GCF, and so as a last-ditch effort we use the factor theorem. So let's begin first with listing all of the possible rational zeros. So we begin with our p over q values. So we're going to take positive or negative p over q. We have positive or negative 1, 2, 3, 6, 9, and 18 as our factors of our p-value, right, which is 18 here. For our q value, our possible values are positive or negative 1, 2, and 4. When we list these ones, these are going to be a little bit longer. I'm going to have a bit longer of a list because I just have so many factors here. But let's take it one at a time. I'm going to take 1 and divide it by every number in the denominator. So I have positive or negative 1, then positive or negative 1/2, then positive or negative 1/4. I move on to 2 then. So I'm done with 1. Positive or negative 2. 2 over 2 gives me 1. That's a repeat. 2 over 4 gives me 1/2. That's another repeat. I'm done with that one. 3 over 1 gives me 3. 3 over 2 is a new factor. A new rational zero. 3 over 4 is another new rational zero, and then I'm done with 3. Move on to 6. 6 over 1 is new. 6 over 2 is not new because that's 3. 6 over 4 is also not new because that's 3/2. Then we have 9, then 9 over 2, then 9 over 4, and finally we have 18. 18 over 2 is repeated, and 18 over 4 is also 9/2. So we're finished now with both 9 and 18, and this is our total list for part A of all of the possible rational zeros. So there are quite a few there, okay? But again, it's pretty simple. You just go through your list. Now, for part B, we're supposed to factor the polynomial. Now, I'm going to give you the hint that in the first day when we were factoring using factor theorem, our possible rational zero list, we don't have to test all of them. We only have to test either positive or negative 1. Okay, so I'm going to give you a big hint and say that one of the zeros should be positive or negative 1. So that means either f of 1 or f of negative 1 should equal 0. I'm going to pause the video now and I'm going to test to see whether or not 1 or negative 1 are zeros of our function. You're just using synthetic division here, so you can pause as well and try these on your own. Alright, so as you can see, f of 1 is equal to 0. So f of 1 is equal to 0, which means that x minus 1 is a factor. And it's a factor of your original quartic way back here. Now f of negative 1 does not equal 0. Its remainder is negative 8. So because f of negative 1 is equal to negative 8, then that means that negative 1 is not a 0, which means that x plus 1 is not a factor. So you can even conclude that x plus 1 is not a factor. All right? Now, what we need to do then, I'm going to erase this work over here. What we need to now do is continue to factor this polynomial that's left over. So we have the polynomial 4x cubed minus x squared minus 27x minus 18. This is a new polynomial that we're going to use the factor theorem for, because here we cannot factor out 2 and 2. We can't use our normal methods for factoring, so we continue to use factor theorem. Alright, now we could continue again to try to find the possible factors of p over q here. We'd make our list and then we would check all of our list, but in this case I'm going to help us out a little bit again because I already know that f of negative 2 is equal to 0. So what this is saying again is that now negative 2 is a 0 of this function here, okay, and we can make x plus 2 now another factor of this polynomial here. So I'm going to use synthetic division again. So when you have something of higher degree, like we started with that quartic, right? Up here we have a quartic. You need to use synthetic division twice, or factor theorem more than once, okay? So we've got negative 2 on the outside here. I'm going to use 4, negative 1, negative 27, and negative 18. So I use the coefficients of this new polynomial here. So I'm going to pause and do this part. Alright, so clearly negative 2 is a 0 of your function, which just verifies again that x plus 2 is a factor. Alright, now we end up with this quadratic left over, 4x squared minus 9x minus 9. Now we don't need to continue using factor theorem because we can just factor this quadratic like normal. When you factor this, I'm not going to do that one with you because this one's pretty simple, we end up with 4x plus 3 and x minus 3 as our other two factors. So when we finally list our final answer here, I know this has been a long problem and a long lesson, but we want to take all of these factors, this x minus 1, this x plus 2, and these two, and put them all together. Okay, so I have 4x plus 3, x minus 3, x minus 1, and x plus 2. Again, if you want to spot check that your answer is correct, you should be able to multiply these constants here. So 3 times negative 3 times negative 1 times 2 gives me positive 18. 4x times x times x times x should give me 4x to the fourth, and it does. Alright, so this is a reasonable answer at least, and that's how you know that you did it well. Alright, please try example 4 on your own. Recognize that this is a hint here, f of 6 is equal to 0, so go ahead and list all of the possible rational zeros, check with the key, and then factor the polynomial. Alright, nice job, that was a long one. I'll see you in class tomorrow.